also here with me. And over the next 30 to 40 minutes, we are going to talk about how to overcome power challenges in IoT devices, and how to make your devices last longer with the same battery that you are using currently in your device. There are certain ways in doing it. So we'll try and share as much as we can on that. Before starting, let me just speak a little bit about Axcelta for a minute. We are an Internet of Things, IoT company based out of Hyderabad, and together, me and my partner, we have, over the last 20 years, together got more than 40 years of experience in product development, and we have developed solutions for remote asset management. So we have already got a solution on remote sales management, which we have already. The first client is Coca-Cola India, and we have another remote security management solution which we are going to launch in a month or so. Osmosis is our platform on the cloud, which you can integrate any device, which is already live in production, having hundreds of devices already connected to it. And of course, our platform is also, uses big data analytics and intuitive UI to, so that you can very quickly create your reporting and relevant business use case reports that you want. And this initiative, why we are in front of you, is because of Axcelta Academy, which we launched in May 2014. Since then, we have come a long way, and we have regular IoT trainings and stuff, and we keep on doing these webinars where we want to share information, whatever we know on IoT technology areas. These are our profiles. I think won't go into details, but we have got deep experience in product development and stuff, and now we are trying to leverage that in building our own products and service offerings as Axcelta. So I hope everybody is able to hear me clearly. Can you just type yes, yes there, in the chat? So how this presentation is going to work is that I'm going to just introduce you all to the concept of IoT a little bit, and then I'll pass it on to my co-founder Manish, who will then take you through this webinar. So this is essentially Manish's webinar. He will go through the entire, technology behind saving power with you. And if you have any questions, which you will have while we are going through it, just keep typing your questions. So at the end of it, we will go through all the questions as much as we can and try and answer as much as we can. And if you don't know the answer to some question, we will get back to you later. So, just keep typing your questions and just keep sharing your thoughts. Also, if you can just tell me whether you are able to hear me clearly by typing in the chat window yes right now, that will help me. Sure. Okay. So that's great. So let me just move on very quickly. So this is the IoT. So I want to just explain to you what we mean by IoT business, so that we speak the same language and we talk about concepts in the same wavelength. So these are some of the white good devices, right? Everybody recognizes them: a TV, a washing machine, a dishwasher, and stuff. So I want to make these things here as smart things. So what all do I need to make it smart? So as human beings, we are smart, right? So we have certain senses built into us by somebody. So when we try to make these things smart, we do the same thing. We have, as a human being, we have an identity, and then we have certain senses, right? So when we want to make something smart, we give that thing an identity, maybe an IPv6 or something like that, and we also give certain sensors which go into this thing, right, to be able to sense things. So this sensor part here, what kind of sensors will go in, can only be defined by a domain expert of that thing. So for example, a fridge. Let's say the example of Samsung fridges. Okay, Samsung is one of the large white good manufacturers. So Samsung will know what kind of sensors which go into fridge, what kind of data it wants to capture from the fridge to be able to make sense out of it. So those sensors which will be able to capture the data will be placed inside this refrigerator. Okay, and these sensors will know how to communicate to the outside world also, using some of these protocols like Bluetooth, Bluetooth Low Energy, Zigbee, Z-Wave. And this entire thing which goes into this larger thing is called a node. So this is a key terminology, that node is the thing which goes into the or the device which goes into a thing which you want to make smart. Okay, and typically this node will be very small in size, will be constrained in terms of cost, in terms of power consumption, in terms of the range that it has, and several other things. So essentially, so in a case of fridge, for example, you can visualize that this node receives power from fridge. But in the case of certain other use cases where the node has to be installed in some device which doesn't have power, okay, like maybe a boiler where you want to measure temperature, or maybe in forest in order to detect fire, or inside water somewhere where you want to detect pollution levels, or inside ocean somewhere where you want to detect tsunami wave. So all those constrained devices where you need to have a battery, where the battery should last for months, if not years, right? So, and the size of the device also should be small because it has to fit into all these things. So in your wearable, for example, this node has to be very small to fit inside a wearable. Okay, in certain areas where you want to detect, for example, flow through a water pipeline, which is a very small water pipeline, you need to have again a very constrained node. In several such use cases are there, where the node size needs to be constrained. It has to run on battery power. Its range is very constrained. The kind of processing power it has is very constrained. So this node is typically something which will go into a thing and it will be very constrained in all aspects, generally speaking. Okay. So you have to understand this concept of node. And then this node knows how to communicate to a cloud-based platform. And like, for example, you must have heard about Xively, ThingWorks, Exida, those kind of platforms. And Osmosis is also one such platform which is owned by Axcelta, which is our platform basically. And you can potentially connect millions of devices to this platform. And for example, Samsung will probably sell 100 million white goods. And Samsung has already declared by 2017, anything it manufactures which is over $100 value will be smart or will have this node in it. Okay, so just all those things, communicating the data to this cloud-based platform called Osmosis. And your cell phone also is becoming, the smartphone is becoming more and more into a very important piece in IoT space. It's able to communicate both ways, from the node to the cloud and from the cloud to the node. You can also do actuation from it. You can control your refrigerator or your washing machine or your AC through this. Okay, and this big data analytics is where the ROI for Samsung will come, because it will be able to take decisions based on business, like what kind of washing machine is lasting more. It will have all the parameters of the washing machine coming to it. It can pinpoint, okay, this machine is going to conk out. Maybe repair it before it fully fails and save a lot of money for you as well as for itself. So this is where the ROI for this investment comes for Samsung. And for you, the ROI comes from here, where you are able to control this. And also from a lot of other use cases where, for example, wearables, you are able to control your health parameters and stuff. At least note them down and your doctor can take wise decisions based on that. So a lot of ROI comes from here, and this is also defined by the business. So Samsung will define what kind of report it needs, right? And doctors will define what kind of report they need from patient data. So this is also very intensive, domain intensive data. This node is also very domain intensive. And this upper part of this diagram here is completely owned by the business. The lower part is kind of generic and is, you can use any third-party tools. For example, you can use Axcelta Gateway, Axcelta platform. You can use any cell phone to manage this thing. Okay, so this is IoT business, and today we are going to talk about mostly node and how a constrained node, which has to last for years, months or years with one battery, how we are going to, how we can save power in a node. Okay. So moving on, I'll now pass it on to Manish, who is going to take it from here. Over to you, Manish.
Sure, Piyush. Thanks so much. I'm changing myself to the presenter.
Yeah. Yeah, I'll just make you the presenter.
Not that I've done that. All right. So, guys, good evening, good morning. Now, over the next 30 odd minutes, I'll try and take you through some of our learnings that we had as part of building solutions, and then specifically related to power constraints when you build IoT solutions. So to begin with, let's consider three scenarios. The scenario one is that you've got this IoT enabled garden that you've put with a lot of pots, wherein you've put soil moisture sensor and then connected them in order to get a perfect combination of your water supply based on the moisture that is required. Since it's technically 30%, but the challenge with this solution would be that you can't necessarily keep on changing these batteries on an annual basis. In fact, you would want to have multi-year battery life, and then the entire concept of being eco-friendly goes off if you have the kind of scenario where you need to change these batteries, because we all know all these lithium ion and polymer batteries, they are definitely not very good for the environment. So that's scenario one. Let's consider another scenario. You've IoT enabled your home or your business premises by putting these door sensors right across your building, and then when it was most required, you realize that the battery in the node, like you brought about from a concept point of view, died. And then so the entire purpose of putting that entire stuff, it is gone. All right. Okay. So that's another scenario. Let's consider another scenario. Now you've got this situation wherein you want to monitor health or well-being of an individual. That could be a sick person, old person or something, and you put all the required smart sensors available for that individual, and this person unfortunately meets with the situation, and again at the wrong time the variable battery has gone. Right, you can't really expect that sick person or elderly person to be recharging the battery once too often. Like you would want to actually have at least multi-month battery life to get that kind of assurance that you're looking for. So essentially, as we see in all these three scenarios, the node needs to have multi-year battery life for the solutions to work well. Now, so we've understood the requirement. Now let's try and understand the different pieces that go in. And then to begin with, let's get an understanding of what we mean by a constraint device. So a device could be constrained because of multiple possible reasons. First of all, it could be that the kind of or the amount of code that you can put in the device, because you're putting a small microcontroller there, would be limited to a few KBs or something, and you can't really put too much complexity stuff into that. So it's limited by your read-only memory or the kind of flash that you have. The other constraint would be the state that you can manage in terms of the total RAM that is available, and how much of the in-memory processing you can do around that. The third would be about the amount of processing power. So for example, you need a certain response time to come in, but you don't have as much of feasibility to do those level of computation in that particular time. So the processing power, again, because we are using small microcontrollers from a cost perspective, as well as from the point of view of reducing power, brings us these constraints that come in. But quite importantly, it's also about these available power. We'll try and see the different aspects related to power as we go ahead. But another constraint that comes in around this is the interface or the accessibility. So for example, you want to connect your solution, your device, to a Wi-Fi system. There is no direct mechanism to give that password to it. Or in case you want to upgrade your software through the over-the-air update, because you don't really have operating systems on your constrained devices, the upgrade becomes a big challenge, and then also it brings about some constraints related to security. Now let's try and understand from a smart home perspective the different kind of devices that would exist. So Gartner says that there are going to be, by 2020 or something, about 500 smart devices in a home, in a potential home. So these devices could be categorized into three key pieces. One is the normally powered. These are your gateways. They have a direct power source available. Your appliances like your refrigerator, air conditioner, TV would fall into this category. Your smart meter and other stuff also. There would be another category of devices which could be either powered or battery, but they're not really too constrained from a power perspective. So for example, your thermostats, you can take an example of a Nest over here, or light switches, or your doorbell. It's quite possible they would have a power source available. But the third category is where the challenge is, which is normally battery. So your door sensors, your motion sensors, windows, door locks, body sensors, all these things are your constrained devices from a available power perspective, and then this category of devices is where we want to focus on as far as power management is concerned. Now let's try and take a look at the definition or categorization of these devices based on the Internet Engineering Task Force, one work group which is trying to define this. So what we need to look at is these three categories: E0, E1, and E2. So E0 is wherein you have event-specific energy limitation, and in this case, we'll have to look for something. This is the most constrained from a power perspective, and then you would have to look for energy harvesting. We'll try and understand what we mean by harvesting as we go forward. The other would be that these batteries, these devices would require charging on a periodic basis. The third category would be your so the second category is there is power available, but on a periodic basis you have to recharge them. The third category is about, which is E2, wherein the total lifetime power for that device is fixed. You can't really replace the batteries there, and then those kind of categories need to. And then the fourth category we've already seen, no power constraints as such. Now let's try and take a look at typical devices or appliances that we use which are battery powered. What we've listed out here is an uninterrupted power source, the total typical energy available, and then what the expected battery life is. So UPS would typically get attached to your PC or something, and then you're expecting maybe 15-20 minutes, but the amount of power that is available or energy is quite high. So what this is ampere hour, which is essentially your total energy which is stored in the battery. A toy might have about 5 ampere hour, and then you're expecting typically 4 hours. Home inverter, which is basically from an India perspective, in case there's a light, you might actually get maybe 4 to 8 hours of power. Mobile phone typically you would get 2000 mAh. I'm sure a lot of you would have looked at that. And you expect about 24 hours. Fitness band, typical Fitbit or something, you might have about 700 mAh, and you're expecting about 5 days of availability. And if you try and take a look at the intruder detector, the amount of power available is so limited, which is 400 mAh, because of the cost and battery constraints and other things, and you're actually expecting to get few hours. So essentially what this slide shows is that you are trying to solve a very peculiar problem, wherein you're expecting with minimal battery available, you get multiple years life. So ideal goal would be decades long battery life. Minimum, of course, you would want to have at least a year of battery life on any of these typical batteries. So from a power consumption point of view, we'll talk about standby and operational modes when we get into the electronics and the embedded logic, but typically any device would be operating either on a standby and a sleep mode, or it would be in a normal operation or a active mode. So these are the typical ranges that we are looking for, which is about hundreds of nanoamperes in a standby mode, and then maybe hundreds of microamperes in when it sits in an actual active or operational mode. Okay, having said the context around the challenges that exist and the expectations that we have, what we'll try and now do is try and take a look at the various different dimensions that needs to be managed and controlled, and what kind of strategies can be adapted in order to achieve our ideal goal of multi-year battery life. So what we'll be covering about is different circuits, sensors, how you put together your logic, both from an operating system point of view as well as the firmware. What kind of wireless communication? This is a pretty critical piece in that entire game, which consumes a lot of power. Also, what kind of power sources and approaches that are available for achieving this target. Okay, so some of the possibilities that exist when it comes to electronic circuits. Number one is where a lot of research and development is happening. Is how do you build ultra low powered ICs or microcontrollers, and there is a good amount of development and a new research happening in this space. So if we try and take a look at a couple of latest released microcontrollers, one from Atmel, which they claim is this world's lowest power consuming microcontroller. The range that we are talking about in the previous slide has actually been achieved. So this they claim is 35 microamps in an active mode, and then about 200 nanoamps. So if you are able to actually achieve, right now it's in the sampling mode, it's not yet available in production, but if you actually get something like this, a lot of your problems related to power supply can be taken care of. But this is again a pretty interesting and exciting one. There is an organization which does a benchmarking of different microcontrollers for power sourcing, power optimization and ability, and so this one has been given the highest benchmark score. But this also, given the current state of art and in the given set of controllers available, is also quite exciting. So a few of the strategies that go in, both from a microcontroller as well as the electronic circuit perspective, are one is which is very important, is sub-threshold switching. So just assume that your microcontroller operates on, let us say, 3 volts or 3.5 volts, or maybe 1.8 volts. So a typical super threshold switching would look like this, wherein you would be actually using the voltage is beyond the actual threshold that has been defined for that particular microcontroller from a voltage perspective. But when you get to a sub-threshold mechanism, what you do is you actually give the power to the microcontroller which is below its threshold, and then through that you are actually able to optimize a lot of power consumption for that microcontroller. So this is one interesting strategy that gets used. The other interesting strategy is about power gating, wherein if you think about a printed circuit board, using different circuit mechanisms, sleep transistors and all, you try and make sure that there is no power that goes into that particular section completely. So the typical quiescent current that happens in a PCB gets controlled because you've ensured through your circuit, through this power gating mechanism, that there is no current that is going in. So that's a pretty, in fact, for the security device wherein we expect to get multi-year battery life, we are using this strategy, which has worked really well for us. One interesting learning, I guess some of you from the electronic side might be already aware, is that the power regulators that are there are typically 2 core varieties. Linear uses a direct energy burning mechanism, in order to be able to regulate the power supply to the circuit. But switching uses a different mechanism, and as compared to linear, a switching mechanism is so much more efficient when it comes to power regulation for your circuit. And then we'll definitely need to put in regulators. An ideal scenario would be to avoid them, but wherever we need to ensure that quiescent current specifically, or the actual without any power supply current that is happening to those regulators, is limited. And then last but not the least is using SOCs wherever possible. So quick introduction of SOCs. So SOCs are essentially systems on chip. A best example of an SOC is what goes into a smartphone system. And then essentially what it means is the entire circuit, including all those things that need to be there on that particular PCB, are actually put into a single chip itself. And then also what we have is that a mechanism to add features like your Wi-Fi communication, your Bluetooth or Bluetooth low energy communication, all those things put together, if they are put in a SOC itself, in a chip itself, the kind of power optimization that you get, it is huge, because you're not really losing any energy through the PCB circuits and other things, and it really works well. So going for the SOCs really makes a difference. And one excellent learning that we had around this was the usage of the Texas Instruments CC2540 chip for Bluetooth low energy. It worked really well for us. Moving on, the next piece in that game is sensors. That's probably the most complex piece, because there are two aspects you have to deal with. One is the business part of it, and then the other part is the technical part, or the power consumption part. A few aspects related to sensors is try and go for as much as possible passive sensors versus active. So if you try and take a look at a PIR, which is passive infrared sensor, as the name says, it's a passive sensor. The typical power consumption would be about 6 microns. But for the same purpose, or a similar purpose, it's definitely not the same purpose, but similar purpose, an ultrasonic sensor would actually be consuming this much power. So you can see the scale difference that is there in the power consumption. You might actually need to use a combination of multiple passive sensors in order to achieve this goal. Another learning that we've had is that electronic circuits, fair enough, they're much more efficient and all that, but when it comes to power consumption and ensuring that there is no quiescent current, mechanical circuits or mechanical sensors work the best. And so try and see, don't just get stuck with electronic, see if you can use any of the mechanical sensors. And then the other aspect is of course MEMS. MEMS, I'll just introduce you quickly to what MEMS is. MEMS is essentially building your entire sensor within the silicon. So as the name says, micro electromechanical system. So what we are doing here is that the large circuit, like for example, if you think about a 3-axis accelerometer, it might be, let us say, a few centimeters by a few centimeter cube kind of a contraption if it's a mechanical system. But if it is actually burned directly onto the chip, it becomes really micro scale with the same level of efficiency but much lesser power consumption. So MEMS sensors have been a kind of a boon if we look from a Internet of Things perspective, and then a lot of our current smartphones, and in fact a lot of IoT solutions that we see are possible because of the scale difference on the size by using these MEMS sensors. Some of the examples which we see directly in our smartphones also are your accelerometers, gyrometers, gyroscopes, magnetometers, temperature sensors, and then there could be quite a few. So as you can see, we'll actually talk a little bit more in detail about the sensor. So it has actually been fitted, and it's a complete controller in itself, and then the entire circuit is there with wireless communication mechanism within such a small size. So a quick look at what MEMS sensors, MEMS sensor which is there in the iPhone system. iPhone, I guess 5S has that. It's a ST Microelectronics 3-axis accelerometer. This is the entire piece, and then it's actually been burned on that, and it has the exact mechanism that is required for the larger, bigger piece, but the size has been miniaturized, made it into a micro thing, and then as we'll see, there is a good amount of research wherein people are moving from micro to nano, and then there's a good amount of development which is happening in that space also. That brings us to the firmware. So I'll quickly go through some of those aspects as far as the firmware is concerned. So you can manage your power consumption within the microcontroller at different levels. So it could be at a transistor level, architecture level, system level, or at application level. So for example, your operating system could have multiple frequency switching modes. It could actually leverage a lot of the functionality that today's microcontrollers bring in related to different power levels that they operate in. It could also mean having more power aware systems, so that they know that power is a constraint, and then they can switch between those different levels as needed. So it could be about OS management, power aware logic. One important thing is that use interrupts as much as possible. So wherever you would have those polling loops, you are actually moving within the microcontroller in a continuous active mode, wherein we've seen the kind of power consumption, though it's in microamps, but it kind of adds up. And a very important aspect is try and be mostly in sleep and normally power off. So you can actually, a microcontroller can operate at different levels, and then try and build your logic, build your system in such a manner so that you can leverage a lot of the CPU capabilities that today's microcontrollers have to be able to leverage their low power states, and then try and be power off mode so as to reduce the amount of leakage as much as possible. All right. So that brings us to the next piece, which is about the communication. As I said, communication is one of the largest consumer of power because you're talking about wireless communication happening over maybe 10 to 20 meters, and then this actually consumes most of the energy. So there is a good amount of work that has happened and still is happening in this space in order to optimize that. So we'll look at some of those aspects. So this is a typical network of your wireless sensors that may exist in an industry or a commercial establishment, or in fact in a smart home also. And then as you can see, there are different devices or different nodes or systems which are playing a different role based on most often whether they have a power source available with them or not. So let's look at the first aspect, which is about signaling schemes. Ultimately, when you are building a mesh network with multiple nodes helping get the message across to the final destination through these different hopping mechanisms, the network itself and the topology and how the message goes across from one to the other node, because every time a node has to act as a hopping agent, there's some amount of energy consumption that happens. So there is a good amount of algorithms, approaches that have been created in order to achieve maximum energy efficient routing And then there are certain mechanisms which uses low power GPS, internal GPS mechanisms to create self-adapting and then self-healing systems so as to achieve the shortest route as well as the minimum number of hubs, and then not necessarily getting into issues like implosions and overlap wherein your message can potentially get lost. So it's a research field in itself, but there are certain mechanisms that are available in order to achieve this level of reduction in the communication power required. A look at a thread network. Thread network is essentially from Google. It came to Google through the Nest acquisition. Now it has formed it as a thread group, which is an independent organization having Samsung and a number of other large players as part of that consortium. And then they've released this topology, which I believe is a very important one. We actually get into a lot of details of this as part of the training that we do, the 5-day boot camp and the 3-day boot camp. But here I'll just try and quickly introduce to you that there are multiple pieces like your end device or the leaf devices, then you have your routers, and then a mechanism to switch between your short range wireless communication and Wi-Fi, and then how do you ultimately. So we believe this kind of an architecture or topology is going to get replicated across multiple different protocols that come across. That brings us to what kind of a protocol we use. So as we would probably be aware, there are huge number of options available. I've just listed a few, but we can actually have maybe 2 or 3 times these numbers as far as the number of protocols that are available. So there are protocols like Bluetooth Low Energy, which have been specifically optimized to an extent, which ensures you that multi-year battery life, and iBeacon is a perfect example which uses this, and then it actually gets you that level of power consumption requirement that you have. But there are multiple different protocols available, and which can play a role. And there is of course this 6LoWPAN, which thread as well as the IP smart objects, and then a lot of work is happening around this. And then again, we talk quite a bit in detail about what 6LoWPAN is as part of our training. But this definitely is going to play an important role as far as future networks and future solutions are concerned. Okay, a quick look at the power consumption of the different chipsets from different suppliers, and based on what kind of battery we are using, what life we can expect. So for example, Nordic definitely stands out as far as power consumption is concerned, and by optimizing certain other factors, you can actually achieve almost 4 years of battery life. And this is a very important piece in there, wherein how frequently is my broadcast signal from the BLE device that's happening. So as I increase that frequency, the power consumption increases. As I increase the gap between one and the other, because this would happen in kind of bursts, and then each time you send that broadcast message, the power consumption would happen. So by optimizing some of those factors, you can actually achieve quite a bit of good battery life. All right, so moving on, that brings us to this piece which is pretty critical, and there is a lot of challenges related to that, but also there is a good amount of investment happening in order to ensure battery power which is going to work for IoT solutions. So let's take a look at a few battery properties. First of all, you have an internal self-discharge, which is about irrespective of whether there is any actual usage of that battery or not. The because it's a chemical-based battery, the electrolytes within that they decay, and because of those chemical reactions, there is a continuous self-discharge that happens, which is definitely not going to help you achieve that kind of battery life that you're looking at. Energy density is for a particular volume or for a particular weight, what kind of energy you can get. Recharge capacity, how much every time you recharge, how much recharging happens, every time do you lose some capacity. The number of charge cycles that can happen, how much of peak current you can withdraw from there. Typical behavior of these batteries is if you actually draw more current at a single point of time, then the total available energy that is available for you would go down, which is about lifetime energy. So based on so essentially a discharge, peak discharge, and the lifetime energy are in a way inversely proportional. And also there is a memory effect which certain types of the batteries provide or have, wherein if you do not charge the battery up to the maximum level, it remembers that level and assumes that's the maximum level, and then automatically, because of that memory effect, your power availability goes down. A quick look at how you can achieve this 20 years battery life. This is I've taken from one of the battery manufacturers data sheet. Let us consider a quiescent current of your network as about 9 microamps. There is some pulse based communication that is happening. This is most likely RF based communication. The average current draw, so based on all these factors, you get roughly this. And if you consider other aspects related to self-discharge, you can actually, using about 2400 mAh battery, achieve about 20 years. And in this, believe me, is not something which is not possible. With the current set of technologies available, it is definitely possible. Two factors which impact that, which is if your temperature on which you're operating is higher, you can expect that there is going to be a dip in the lifetime energy, as well as the total power you can draw, as well as the discharge rate, I said, has an impact. Multiple different types of batteries that are there. So they have different energy density, the durability of the cycle, the self-discharge rate, pretty important factor in there. Lithium ion plays an important role when we deal with a lot of IoT solutions, but if you see, they have a 10%. Alkaline batteries, which are not necessarily rechargeable ones, have a pretty decent self-discharge rate. And solid state, which we'll try and understand as the next step, is this, as you can see, comparatively, you get almost 6 times, 5 to 6 times energy density. And solid state batteries are going to be important components or important players in future. Okay, so this is a much more detailed sheet of the battery. So we'll take a look at a few. Lithium ion, as you can see, and lithium polymer, they are definitely much better. It doesn't compare solid state right now because that's still too costly for the commercial deployment. From a cycle life, you can expect definitely lithium ion. So that's why most of your smartphone and rechargeable batteries utilize this. Like I said, rechargeable alkaline, 0.3% important. This is something when you select your set of batteries and then decide on that, you should consider in your solutioning. A quick look at what a solid state battery is. If you consider a lithium ion battery, you would have an electrolyte which is a liquid one. It has some challenges. Most common problem is about safety. But in solid state batteries, what you get is a solid electrolyte. So there is some concept of liquid metal. There are some other concepts that are being developed and good amount of billions of dollars is being invested into building something because of the factor that you get about 6 times of your energy density, and if we are able to reduce the cost of these solid state batteries, they can really make a lot of your electric cars, and IoT also is going to highly depend on that. So some of the advantage, thermal runaway, the safety issue, no flammable electrolyte, of course, solid state, so disposal is not as big issue, which is a big issue with the typical lithium ion batteries. High voltages are possible, and definitely much longer life cycle. Cost is one of the basic challenge. There were some other technical challenges. So combining solid state and microcontroller technology is what we get this solid state film batteries, which we believe are the future as far as power sources for IoT solutions which are constrained with the lifetime energy are going to play an important role. So a quick look at this. So you have your anode and cathode, and here you have a solid state electrolyte which has been put on top of a silicon substrate. So you can essentially just go about and then make this solid state battery as a direct part of your printed circuit board and then utilize that. So because of its high energy density as well as the other features, you can actually achieve a pretty good small circuit, which we'll soon see, and then get you that result. Another important development and research that is happening in this space is about energy harvesting. So in combination with solid state batteries and energy harvesting, the expectation is that you can actually get an infinite time of battery life. So there might not be any need to replace battery when these two, I'm not saying if, because we know that it's going to happen, but when it happens, you won't have to at all have a charging capability. So by optimizing your electronic circuits, by optimizing your wireless communication, as well as with a combination of the solid state batteries and a mechanism for energy harvesting, you can actually achieve that target. So a quick look at how you can harvest energy. One is, of course, your typical solar panels, photovoltaic, which is the source of light. You could have vibrations based energy sources, temperature differential, mechanical movement using the piezoelectric, or you could actually have radio frequency or inductive. So radio frequency harvesting is about bringing in energy by directly harvesting from the radio frequency signals that are there in the air. And inductive is about, like a lot of today's smartphones and a lot of IoT devices have like coil-based induction mechanisms for charging. So there is good possibility around that, and if you see, there is the kind of voltage you can get is also definitely not bad. And then from a power output or energy available perspective also, your typical IoT devices would run well with this kind of power source. So right now the challenge might be about the size or about the cost of these systems, but down the line energy harvesting is going to work really well. So this is how the whole thing kind of comes together. You would have your different energy harvesting mechanisms. You would have a transducer which would help convert from those energy harvesting into electrical power. It gets stored in your solid state system, and then through ultra low power wireless communication, you actually are able to achieve the entire circuit, which is going to last for years. Okay, like I had said, that I'm going to introduce that IE-based system, which has been leveraging or has used this technology. So as you can see the size, it uses MEMS sensor. It uses solar cell from a harvesting point of view. It uses the SIMBIT inner chip, which is nothing but the solid state film based battery, and in combination of that you are actually achieving a sensor which is directly placed in the eye and helps interocular pressure management for glaucoma patients. A similar concept, I guess some of you would have heard, is about smart dust, and if you see it's quite similar to what we've seen in the previous slide, and a combination of your harvesting and other things. All right, so that brings me to the last slide of the session today, and then we'll try and get into the questions. This is how the future would look like. I don't know whether it will happen in 2020 or 2025, but we believe this is how the entire IoT systems or IoT would become ubiquitous and part of our life by getting to the nanoscale. So there is work happening related to nanoscale sensors. There are multiple different possibilities that are there. Already there are, from a biological health perspective, already some nanoscale sensors are being used, but not as much from a smart home or smart health perspective, but there is good amount of research happening. There is, from a communication point of view, a lot of work happening related to leveraging something what is known as ultra wideband impulse. So as you can see, when you send a message, there is a spurt in the power consumption. So what this ultra wideband does is that because there is the band is quite big, the frequency at which the data is sent is quite slow, and then the ultimate power consumption gets reduced significantly. Some kind of rocket science stuff also, frictional stuff, or you can say, so molecular communication, wherein you would have the molecules in a real life scenario or in the real world, molecules interact with each other, and they pass energy from one to the other. So the idea is to use that same mechanism for the communication using electromagnetic waves, which are again in the terahertz or tetrahertz frequency band for this communication, as well as quantum communication, which leverages the quantum vibrations that happens from a communication perspective. So sensors, nano, then there's, from a communication point of view, leveraging nano. So essentially, if you see, we are moved to micro, and then now the future looks like is going to be nano as far as the IoT stuff is concerned. Similarly, from a computing perspective, good amount of research happening on nano computing, which essentially, if we see, is also which gets used for the communication that happens in the neurons in the human body. So as such, from a computing point of view, by leveraging resonance, which is directly a basic property of these molecules and atoms, you're actually aping and then trying to get as close as possible to how the body gets intelligence and uses it. MEM resistors as they call it, again at a nanoscale, they have a unique ability to prevent electronic current, but also have a ability to remember what was the last electric current that was passed. So from a computing and building huge amount of computing ability at a nano level, there are certain stuff that is happening in this space. So this is what we should watch out for. It's still probably another 5 to 10 years before any of this comes into place, but we should be cognizant of these technologies, and some of them will already start seeing getting commercialized. So that brings me to the end of my session. What I'll do now is send a poll while we work through the questions. I'll send a poll so that you can give some feedback to us. All right. So thanks so much for your feedback. We'll try and use this for our next sessions. Let me try and pick up a few questions. The first question that I see here is why can't we use smartphone as a gateway? That's coming from Vikram. Yes, smartphone does get used as a gateway, specifically when we are talking about wearables. Definitely it plays an important role, and to a large extent in smart home also for specific use cases. Smart home, smartphone does act as that, but there would be use cases which would require a physical gateway to be there. So if, for example, you have a security system in place, you can't necessarily depend on a phone because you'll probably be carrying it. Okay, so Kavya is asking, can you compare this code with standard Atmega? So I don't have the exact number, but I would suspect Atmega 328 would be somewhere around 25 to 30 as far as the scoring from that organization is concerned. All right, so this question is from Jerick. How to achieve maximum power efficiency using MEMS? To keep sending IMU that has to keep sending telemetry data to the mobile using Bluetooth Low Energy and still survive long. What sort of power supply should I expect such a system to accommodate? So Jerick, thanks for this question. Maybe we can connect offline. There is some amount of more analysis we'll have to do. But I believe using MEMS and Bluetooth Low Energy, we can actually achieve this. We've in fact tried it for one of our use cases, and then we believe it can work. All right, so let's see if there are any questions. So there is a question on, I have done last programming about 5 years back, and would attending this workshop about sensors and would it help? Yeah, absolutely. In fact, the way we've structured the tutorials and built up the system, anyone who has a good learning ability and some technical bent of mind can benefit significantly by doing this workshop or training that we do. And we've trained 550 plus people till now internationally, and we've got an amazing feedback from them, and everyone has enjoyed the sessions. Okay, so what about the battery we currently use? Is there a way to optimize it? Absolutely. So battery source is one aspect in the entire game. So you can use your optimal use of circuits, optimal use of different microcontrollers, as well as optimal program logic can get you the result, Tejas, as far as the battery is concerned. But as far as the battery's individual property is concerned, with the existing battery, you can't necessarily change that. All right, next question from Kavya. If we use Wi-Fi, Bluetooth, Zigbee in different nodes, will it make the communication system more power hungry if the nodes has to communicate with each other? So Kavya, this is something which we actually go into pretty much detail when we do the training. But definitely I don't think these systems are going to talk to each other. So right now there are no standards or no technology available which would get your Bluetooth to talk with Zigbee, because the entire network stack that gets used in these protocols is different. All right, so question from Raja, maximum battery life when using GSM, SIM 900A. So one thing I can definitely tell you, Raja, is that you should not attempt to build a battery powered solution using a GSM module like SIM 900A. So there are challenges. We in fact burned our fingers when we were first building our security solution. So you should build it in such a mechanism that uh, your modem or your gateway has a continuous power source. It can go back to battery as a backup, but not as a primary power source. It is what we believe. But again, we'll have to understand more specifically about your requirement to answer that in more detail. Any one article, website which gives end-to-end knowledge of this? I guess not, Zube. There is good amount of experiential learning that we've put in, as well as a good amount of research. So I guess there won't be anything, though we'll be making this available, this webinar available as a video, and then you can always reach back to us if you have anything that you have specifically in mind. Yeah, so again, Namit, these are all different alliances. So all join or all seen alliance, OIC, there are quite a few different alliances that are there, and each of them have their own strength. We actually go into these alliances and the hardware as well as software platforms like your ThingWorks, like Exida and stuff as part of our training. And in case you attend that, I think that could be interesting for you. Will we be covering WSN routing module in training? Not necessarily, Raman, because the focus of the training is to get an end-to-end perspective and get your hands dirty. So just a quick background on what we do as part of the training is that we help you. We take a use case. The use case is of a logistics company which is transporting perishable goods across the country and facing challenges related to too much of damage happening for the goods. So how do they IoT enable their fleet with sensors, with GPS, with the fleet tracking mechanism in order to solve that challenge? So what we do is we give this use case, we give the hardware system, we provide the software environment, and then the requisite help and help you solve that. So the idea behind that training is to give you an end-to-end hands-on feeling so that then you can go about and then go deeper into your specific technology. If you're building a solution, it equips with you with at least 3 or 4 months of head start. And if you are employed and are an expert in, let us say, embedded field, or you are an expert in the cloud systems, it gives you the view of the other side of the world, so that when you're solutioning, when you're talking to people or talking to clients, you have that end-to-end perspective. And then this is something which we realized when we trained about 100 plus people at Intel. They are your core SOCs and microchips designers, and they really loved the program because they never knew that bigger picture. And when they did those big data analytics and connected those Arduinos and then sent data to the sensor, it worked really well for them. All right. So what is the time frame for training? So what we do, Rama, is that we conduct over the weekend. So our next batch starts on 25th of April at 6:30 p.m. India time. So we'll be doing on 25th, 26th, 27th, followed by the next weekend, which would be the hands-on session. There is another weekday batch also, which starts on 29th, by the way. So you can go to our site and then get that that perspective. Kavya, thanks for the feedback. We are happy that you like the program, and we definitely look forward to share more information with you and more insights. And of course, we look forward to having you part of the boot camps that we do. All right then. So thanks so much, and